We're now in a position to enter our last portion of the class, which is thermodynamics. Now, here, one thing to pay attention to is when we talk about thermodynamics, what we really mean are thermostatics. And the reason for that is we're always going to be looking at situations where we're in thermal equilibrium. If we weren't in thermal equilibrium, basically what would happen would be what? Well, we would have to deal with math that is well beyond the limits of this class, things that are actually very, very difficult to deal with, where people are actually still coming up with ways to actually be able to deal with these situations. So again, whenever we talk about thermodynamics, what we really mean is actually thermostatics in the case where our system is going to move, but we have to have thermal equilibrium initially and thermal equilibrium at the end. So our system has to establish some sort of equilibrium. So we can't really talk about what happens in between, only at those equilibrium positions. So now, before we get into really thermodynamics and start talking about all the laws of thermodynamics, we first have to talk about everything that's going to build up to that. And the first place we're going to talk about is thermophysics. So basically, thermophysics deals with temperature. Now, when we talk about temperature, what we really mean is the statement of thermal equilibrium. So what do I mean by that? So what I mean is, let's say here's outside, which I haven't really been outside in the last couple days, but whatever, we'll live. So outside has a temperature. So last few days has been what, like basically in the 50s. So this is going to be my cold system. So I'm going to say this is my T cold, right? And then I'm going to go from inside. So this is my other system, where this is going to be my inside. And this is outside, which is at a much hotter temperature. So this is going to be my T hot. So again, outside's been about 50s. My house is usually about 70. So it's about a 20-degree difference. So what I'm going to do is, from my inside, I'm going to take a thermometer. Okay, so here's my thermometer, which is now registering, again, 70 degrees at the hot temperature. And I'm going to bring this thermometer and I'm going to place it outside. And then I'm going to walk away and then I'm going to come back at a later point in time. So what's going to happen then is that at some later time, this thermometer is now going to tell me exactly what the temperature is outside. And the way that it does that is it establishes what's known as thermal equilibrium. So it does that by basically saying that here I have my hot source, which I brought, in this case it's a thermometer. I brought it outside. It's now the hot source and I put it into a cold source. So once I leave it there, what happens then is that energy flows from my hot source to the cold source. This is what we call heat, until eventually these two systems become exactly the same temperature, which is what we call thermal equilibrium. So when we measure temperature, what we're saying is that two objects have exactly the same amount of temperature, whatever the meaning of temperature is, but these things have exactly the same temperature. And again, the way that this happens is energy flows from a hot source into a cold source. This is what we call heat. It's the flow of energy from one system to another system, until eventually what happens then is that this thing is going to reach T cold, and this is going to reach T cold as well. Now, again, the way that this usually works is that this one's temperature is going to decrease while this one's temperature is going to increase, until eventually these two things are going to become into thermal equilibrium. Now, of course, here, when I bring my thermometer outside, I'm not going to increase the temperature of outside, mostly because my thermometer is something small. Outside, the air is massive, a huge amount, compared to the thermometer, which basically means that even though the outside is gaining energy, it's barely gaining any energy at all, because this thing had barely any energy to begin with. So the temperature of outside doesn't necessarily change, or if it does, it's only going to change by a very small fraction that I'm just not even going to notice. So again, when we think of temperature, right now temperature is not a definition of what it is, but it's an operational definition. And this operational definition basically just tells me that it is the ability for two things to establish equilibrium. So that's all temperature is. So my ability for these things to establish thermal equilibrium allows me then to reliably say that this thing has exactly the same temperature as this one. Now, if that was not true, If this thing would never go into thermal equilibrium with this one, then I could never know what the temperature of any object was. Right? So if I took my thermometer and I put it outside, but these two things never actually established thermal equilibrium, I couldn't say my thermometer then had exactly the same temperature as outside because I wouldn't know. This one thing, we had a completely different temperature than this one. So again, our definition then of temperature is purely an operational based, which is the ability for two things to become in thermal equilibrium. So that brings us to what's known as the zeroth law, the zeroth law of the zeroth law of the first law. Zeroth law of thermodynamics. So what the zeroth law of thermodynamics says is that, zeroth law, is that if I have multiple systems, so let's say I have one system here, system A, and I have another system, system B, and then I have another system, system C. If I say touched system A to system C, and I let these two things establish thermal equilibrium, such that the temperature of A was equal to the temperature of C, and then I touched B also to C, until these things also came into thermal equilibrium, such that the temperature of B was equal to the temperature of C, then this tells me then that the temperature of A then must be equal to the temperature of B. This is what we call the zeroth law of thermodynamics. So again, it's just an operational based statement. So it just means that two or more systems which are in contact with each other, which all eventually will end up having the same temperature, are then thermally equilibrium with each other, meaning again they have exactly the same amount of temperature. Right. So this is how we're going to define temperature for now. Now eventually, as we move through the semester, at least through this section, we'll eventually define what temperature actually is. But for now, this is just our idea of what temperature is. So these two things are in thermal equilibrium. At whatever temperature may be, we don't know. All we know is they have exactly the same amount of number. So great. So now, well, we know the zeroth law, and that these things are allowed to come into thermal equilibrium with each other. That allows us now to build temperature scales. So basically, now that we know things can be in thermal equilibrium, how do we describe them? So what kind of numbers are we going to put onto them? So from here, we want to talk about temperature scales. So, now, the way we define a temperature scale is basically we're going to say one number has one meaning, one number has another meaning, and then basically build a scale from there. Now, it sounds easier said than done, and the reason that it's easier said than done is, for example, we as humans, we don't measure temperature reliably. And what I mean by that is, last week, it was like in the 80s and the 90s, so it was ridiculously hot, right? But going into that, we went from lower temperatures, right, from like 30s up into 50s, so 50s felt much warmer than the 30s and 40s. Then by the time we got to the 80s and 90s, we were sweating to death, at least I was, because I'm always not happy when it's hot out. To now, this week again, back into 50s, and what happened? So 2 weeks ago, we were warm at 50 degrees, right? We're all running around in shorts and things because it's no longer in the 30s and 40s. To 90s, back into 50s, and now that's back in 50s, we're all wearing long pants again with sweaters. Right? So even though the temperature, the thermal equilibrium is exactly the same, 50, but us as humans, the way we respond to that is different because of what happened before that. Again, everything is relative. So we went from low temperature to a higher temperature, so we felt warmer, so we could take more clothes off. Then we went to a high temperature, back down to a low temperature, in which case we now felt cold because our reference point was something much higher. So everything is actually relative. Now, the only thing is, if we build our scale too small, meaning if I was standing over here, and then I walked over here, if my scale is too small, then a 1 degree difference from that side of the board to this side of the board will be something that's basically unnoticeable. Right? So if I had a scale whose degree increases is so ridiculously small that I can't really reliably measure, again, 1 degree change going from one side of the board to the other side of the board. So if we had, say, a bigger scale change, then that would allow us then to more reasonably be able to detect a change in degree, because our definition of degree is now separated by a much greater amount, which allows us more to reliably be able to describe this. Now, but again, the way we determine our temperature scales is we're going to pick one number, pick another number, and then basically build our scale from there. So historically speaking, the first temperature scale that came out was what's known as the Fahrenheit scale. We call that degrees Fahrenheit. Right? Now, let's talk about the pros of Fahrenheit. So the pros of Fahrenheit are USA uses it, meaning that you and me and pretty much everybody from the US are more familiar with this. So when we hear things like Celsius scale and other types of scales, we're like, okay, that's great. I don't know what that means, but we have a good idea of what this means in Fahrenheit. Are there any other pros? No, not really. Other than the fact that pretty much we use it and a lot of the rest of the world uses it because we use it. So let's talk about some cons. So what's a con? Well, a con is that this thing has no scientific meaning to it. Alright, so what do I mean by that? So what I mean by that is, what number does water freeze at according to Fahrenheit scale? Well, 32 degrees. Right? This is when water freezes. Where does it boil? What is it, 212? It boils. Why those numbers? Why? Well, I don't know. I mean, doesn't make much sense why you'd call freezing 32 and boiling 212. It just happens, right? Just the way they did it. Other con is that pretty much most of the rest of the world doesn't use it. So, for example, anywhere in Europe or Canada or other places you go to, they all use Celsius scale, so it's hard to convert back and forth, at least for us that are more used to this type of scale. So this, again, was the first attempt at creating a temperature scale, at least the first that I know of. Not much of a great excuse, but hey, that's all we got to work with. So in this case, again, there is no scientific meaning to it. These numbers are basically just random. Okay? We just have random numbers based off of these. So, and another con about this is that the, change in a degree is small. Okay. So how do I know it's small? Well, I know the difference between this one and this one is 180, right? So basically between where water freezes and where water boils, there's 180 degree changes going from that point to that point, which basically means that a change in degree of Fahrenheit is very small. So in this room, if I change the degree in Fahrenheit by simply 1 degree, I wouldn't really notice it, unless it's like already in the 90s and you go from 90 to 91, then no, I'll definitely know that you changed it. But otherwise, I wouldn't know in a typical case. So the next attempt is the Celsius scale, which we call degrees Celsius. Right? Some pros of this. So use the same color. So pros of this is that, again, as we said here, most of the rest of the world uses it. So most of the world uses it. And another pro is that it's actually more scientific, right? So this one is more scientific. So how is it more scientific? Well, let's think about it. So where does water freeze in Celsius scale? Well, that is 0 degrees Celsius, right? So we said that at 0 degrees Celsius, water then is going to freeze. Sounds like a good rational place to start. Where does it boil? Well, 100, right? So here, we're choosing two things which happen naturally in nature. Again, water freezing and water boiling, and we're taking those as our reference point. So we're calling 0 at where it freezes, 100 at where it actually boils, and then building our scale from there. So what that means then is that this scale isn't as fine as this scale, because again, here there's 180 degree changes between water freezing and water boiling. Here there's only 100, which means that a change in Celsius is a greater amount than a change in Fahrenheit. In fact, it's actually 1.8 times. Now, what are some cons of this? Well, a con, so where's my cons here? Is it is not fully scientific. How is this not fully scientific? Well, it turns out, we're going to get to this later, I'm actually going to answer the question of what we stated in the beginning, which is what actually is temperature? How do we actually define temperature? Well, it turns out temperature is actually related to kinetic energy. So it turns out that if we are looking at the particles moving around in air, at least in this room, then what temperature is then it's the average kinetic energy at which all the particles have in this room. So this is what temperature actually is. So Lord Kelvin decided he was going to come up with his own temperature scale, which then took that into account. So what he said was that what? There had to be some absolute zero based on the fact that when things get cold enough, the kinetic energy is basically going to go to zero, which means the temperature should actually go to zero. So this is what we call absolute zero. So the most scientific that we can have is what's known as the Kelvin scale. So it's talking about Kelvin. Now, semantics, Kelvin is not degree Kelvin, it is just Kelvin, unlike Fahrenheit, which is degree Fahrenheit, and Celsius was a degree Celsius. So, for example, this is 32 degrees Fahrenheit. If I was talking about Kelvin, it would just be 32 Kelvin. So, so the pro of this is that it is fully scientific. I'm going to put fully in quotations here. And again, what this is saying then is that when the kinetic energy goes to zero, the temperature goes to zero, which is what we call the absolute zero. Now, what Lord Kelvin also did is he decided that this was a pretty good idea, right? Taking a 100-degree change between freezing and boiling, and he wanted to keep that in his temperature scale. So basically, that then corresponded to what? That when water boils, then we have 0 degrees Celsius, which then corresponds to a temperature of 273.15 Kelvin is when water boils. And then it's 283.15 Kelvin when the water freezes. And then when water boils. So here, going from Celsius to Kelvin, it's actually just an additive change. So when I have 0 degrees Celsius, that corresponds to 273.15 Kelvin. But when I go from Fahrenheit to Celsius or Celsius to Fahrenheit, it's additive and multiplicative. So we have to be a little bit careful of that. But now, okay, so here I put fully scientific because it's actually truly not fully scientific. And the reason for that is, now we can't blame Lord Kelvin for this because it came afterward. But if you take quantum mechanics into account, what quantum mechanics basically says is that we can never know definitively something's place and something's momentum, which basically means it's kinetic energy. So what this means is that quantum mechanically wise, there's always going to be random quantum fluctuations, which is causing a particle to either oscillate or move or have some sort of fluctuations, which means that we can never get fully down to 0 kinetic energy. There is some uncertainty to it, some quantum fluctuations that are going to cause this thing to not go to 0 Kelvin, which means that there is going to be, 0 kinetic energy, which means there is no actual absolute zero. We can never get fully down to 0. And it's actually what's known as the third law of thermodynamics, which says that no system can achieve absolute zero. So because of quantum mechanics and these quantum fluctuations, due to the fact that it can never be at one particular point in space with 0 momentum, we can never know the two of those things simultaneously, which then allows this to never fully be able to reach 0 zero kinetic energy. So if it reached zero kinetic energy, we would have zero idea where it would be. So the uncertainty in the position of this object would be infinite. So we'd have no idea where it was. Or if we knew exactly where it was, then the uncertainty in the kinetic energy would also be infinite. So in this case, there is this quantum uncertainty, which again, it doesn't allow this thing to actually be able to reach zero. So again, this is why it is fully scientific, because again, he didn't know about quantum mechanics, so he didn't know this part. But again, this is where the absolute zero comes into account, because again, temperature is related to kinetic energy, and this is something that we'll derive later. So these are temperature scales. So again, temperature scales are, we basically pick 2 points, Fahrenheit, 2 random points. For Celsius and Kelvin, we take 2 points that actually make more scientific sense. Set those then as their basis of our scale, and then divide that into even steps, and then we build our scale from there. So now that we know how to create a temperature scale, how do we actually make something which is going to measure then the temperature? Well, we create a thermometer. So a thermometer is something which is going to measure, again, in our case, this thermal equilibrium. So let's talk a little bit about thermometers. Now, there are multiple different ways to make thermometers, but let's talk about some restrictions to our thermometers. So what do I mean about restrictions? What I mean about are things like safety. So what are some things that are either going to put safety restrictions on this, or things that we don't want it to do under normal conditions? Well, one thing we don't want it to do is what? Freeze. Right, so we don't want to make a thermometer out of something like water, because under normal conditions, when it gets cold enough, water is going to freeze, it's going to turn to ice, and then it's basically going to destroy our thermometer. So we don't want whatever it is that we make our thermometer out of to freeze in normal, everyday type of circumstances. Having said that, we also don't want it to boil, right? So again, we don't want it to, be able to boil under normal conditions. Another thing is we don't want it to be toxic. So what do I mean by that? Well, I mean is, let's say I want to take the temperature of one of my kids, and I give them a mercury thermometer, and my kids love chewing on things, so they're going to chew on it. What happens if they break the glass? Well, not only do they now have glass in their mouth, which they can now cut the inside of their mouth, or worse, down through their esophagus and further, but they're also going to ingest some of the mercury, and mercury is highly poisonous to people. So we want to build something that doesn't boil or freeze in normal circumstances, and we want to make something which is non-toxic, and hopefully something which is, again, pretty durable. So we want to build something that's not going to break, again, under usual wear and tear. So these are some of the restrictions that we want to put on our thermometers. So having said that, what are some typical thermometers that we can make? Well, one is what's known as a fixed volume thermometer. So basically here, we're going to talk about this a little more in a second, but this is when we take a thermometer, something like this, and then we fill it with some sort of fluid, which then is going to expand or contract, i.e. it's basically going to change its volume under changes of temperature. We'll talk about how that happens in a second. So basically by measuring the changes in the volume, we can then determine exactly what the temperature is. So here initially, let's say this thing is calibrated to 70 degrees Fahrenheit. So if it goes up from there and I can measure the amount of volume which has changed, that will then tell me the final temperature. Or if it contracts due to the fact that it's cooling down, again, I measure that volume change, and then it's going to tell me what that temperature is. So these days we don't use mercury anymore. We pretty much use things like alcohol. And again, alcohol won't boil or freeze at a typical everyday type conditions that we're usually going to look at. But this is what we call a fixed volume thermometer. Another type is a thermal resistive. So thermal resistive thermometer. So what does this mean? So this means that basically we set up a circuit. And inside of that circuit, there is typically going to be a resistor and some sort of capacitor. So this is our resistor, this is our capacitor. And what we know is that as temperature changes, resistance changes as well. So basically what's going to happen is we're going to have some current running through our circuit, and then we're going to have a temperature dependent resistor. And then basically as the current goes through the resistor, the resistivity of the resistor is going to change, which means the current is going to change. So by measuring the current and measuring the changes in the current, we can then measure the new resistance, which means we can measure the new temperature. So this is one way. Another one is what's known as a thermocouple. So in this case, the idea is basically the same, except we're going to have a temperature-dependent capacitor. So basically, again, the idea is down at the same. You have a current running through. This one is no longer temperature-dependent, at least not as much as this one is. And then again, when you have changes of capacitance, then that causes the current to change, which then causes you to be able to measure that temperature under these changes of current. Another one is night vision. i.e. infrared spectrum. So where does this one come from? Well, this one comes from the fact that anything that has a temperature, such as me, the earth, right, the lamps, my floor, anything that's at a temperature actually gives off electromagnetic radiation, gives off light. Now, it turns out that the light which is given off, the peak or the most probable frequency which is given off, actually corresponds to a temperature. So basically meaning that if I plotted the wavelength versus the probability, I'm going to get something that kind of looks like this. Okay. Which basically means that there is one particular frequency, which is known as the characteristic frequency that you're giving off, because it has the highest amount of probability. Now, for something that has a temperature such like a human, where we're supposed to be around 98 degrees Fahrenheit, we're usually going to give something off in the infrared. So basically, by measuring the energy or the wavelength of the light which you're giving off, you can then measure this temperature. So this thing has a direct proportionality to a temperature. So basically, anybody who's ever gone hunting before and used infrared or watched movies where you see things glowing in red using these night vision goggles or the infrared spectrum, those are things that are hot. Things that are actually colder have a lower temperature, which means they have a lower color. They're usually going to be more like a bluish or purplish according to these infrared spectrum. This is how they actually back... It's kind of funny we're talking about this now because we have the COVID-19, but COVID-2 I think is what it was, which was SARS. This is how they actually identified people in large crowds in China who were infected with SARS. So pretty much what they had is the military up high on top of buildings looking at the crowds using infrared scopes, so using night vision goggles, and anybody that was glowing redder, i.e. they were hotter, they would then go and take that person and then basically put them into quarantine. So, again, kind of funny we're talking about it now because that was a COVID and we have a COVID now, and that's why I'm doing this at home and while you're watching these videos. But, so good. So these are, again, typical types of thermometers. Again, the fixed volume, thermoresistive, thermocouples, and night vision or infrared spectrum. These are all particular ones that we can actually use. So let's talk a little more about these fixed volume. Let's talk about thermal expansion. This will be the last thing we talk about. So thermal expansion says that all objects are going to either elongate or contract under changes of temperatures. So let's say here's my object, and let's say an initial temperature. This thing has an initial length to it, L initial. But let's say now I increase the temperature, so this is going to increase to some hot temperature, so T hot. What happens then is that this thing is going to increase its length by an amount of delta L. So what thermal expansion says is that the increased length of delta L is equal to alpha, which is some constant, times the initial length times the change in temperature. Okay? So alpha here is what's known as the coefficient of linear thermal expansion. Now, like most constants, this is just a constant which actually depends on the type of material that I have. So, for example, lead versus wood versus concrete versus etc. All of these are going to have their own different alpha values. Now, again, since this has a length here, this has a length here, alpha then has to have units of inverse temperature. So this thing then has units of usually 1 over degrees Celsius, which is equal to 1 over Kelvin. Remember, 1 degree change in Celsius is exactly the same as 1 degree change in Kelvin, since they're all based off of a 100-degree change. So those two things are the same. So all this says then is what? If my final temperature is greater than my initial temperature, this delta T is going to be positive, which means delta L is going to be positive, so this thing increased in length. If my final temperature is less than the initial temperature, delta T here is going to be negative, which means that this is also going to be negative. So I have a decreased change in length. Now, what's also happening is not only is the length changing, but the area is changing as well. So we can also have an area expansion. So what the area expansion says is that what? If I have an object which here has an initial area, A0, under increased change of temperature, this thing is going to increase to a new area, where this amount of change in through here is the change in area, delta A. So this says that the change in area is equal to twice of alpha times the initial area times the change in temperature. But if the area is changing and the length is changing, well, that means the volume is changing as well. So we can also have a volume expansion. So in volume expansion, what this thing says then is that the change in volume is equal to beta times then the initial volume times the change in temperature. Or if I have a solid, this is then equal to 3 times alpha times the initial volume times then the change in temperature. So beta then is what's known as the coefficient of volume thermal expansion instead of linear volume expansion. So this is then for thermal or volume thermal expansion. Now this one's typically used for something like a gas because gases that don't really have an area change, they're going to have some sort of volume change, and they're definitely not going to move in only one direction. They're going to move in basically all directions, unless I somehow can confine a gas to only move in 2 dimensions or 1 dimension, which is basically impossible. So this one for gas typically only has a volume thermal expansion, where something like a metal, right, some sort of solid, we could confine it to move only in one direction or another direction. So these are thermal expansions. So again, any object actually changes its size under thermal expansion. So again, if it increases temperature, it usually expands. If it decreases temperature, it's then going to contract. So these are reasons why you're only supposed to build during moderate temperatures. I'll put some pictures of this up onto Blackboard so you can kind of see why. But basically, the reason for this is that if you build at any other time, i.e., so if you build, say during the winter time, what'll happen is when you build it, and then you move into summertime, the object is going to expand, and by the time it expands, it can basically rip down the building, right? So if you don't build enough leeway into there that the thing is going to allow to expand, you're going to put a lot of stress and strain, something we won't talk about in this class, but basically you put a lot of force onto it, which can actually cause the system to fail and say break, right? Or if you build it in the summertime, it's going to be at its maximum length, but by the time it makes a wintertime, it's going to contract. By the time it contracts, again, it's going to have a lot of stress and strain, so eventually it could snap, right? So This is why you get things in the roads like thermocouples, right? So basically what a thermocouple is, so if you look at a bridge and you drive over it, you'll see that you have kind of like these fingers that move in and out with each other. So what this is allowing you to do are things like the blacktop and the metal and stuff to move. So as it thermally expands and contracts, these are actually moving in and out from each other, which is going to basically take away all that stress and strain, which is going to cause the system to not break and not fault. If you're looking at something like a train track, so in this case, here's your train track, but typically they're going to build pieces in that look like this, where the train track actually separates, where again, this is going to allow the track to expand and contract without actually breaking the track itself. So again, when you actually build something, you have to take this stuff into account. You have to take into account thermal expansion and contraction, because if you build things too tight, again, whether it's in the summertime or in the wintertime, it's going to have too much stress and strain that it's going to break apart basically over time. So you should technically only build in the winter time, or sorry, in the fall and in the spring, where it has moderate temperatures where the contractions aren't going to be too much in either direction. Now, other places that thermal expansion comes into account are what we call bimetallic strips. So basically, one thing you can do is you can take two metal pieces and basically attach them. So each one has a different alpha value. So let's call this alpha 1 and alpha 2. So what will happen is, as I increase the temperature, the one which has the greater thermal expansion coefficient is going to change the most. So basically meaning if alpha 1 is bigger than alpha 2, as I increase temperature, this one wants to grow further than this one does, which basically means that my system is going to go from looking like this to a bent system. It's going to bend basically in this direction, because this one doesn't grow as far as this one does, but I have them attached to each other. And then, same thing, if I cool it down, what will happen is, so this is when T increases. Now if I cooled it down, what will happen is this one wants to shrink further than this one, which basically means that now this one is going to pull it. So in this case, it's going to go into this direction when I cool it down, where T then is going to be lower than what its initial temperature is. Now these are used actually as thermostats. So basically in your thermostats, what will happen is you have this bimetallic strip, where that bimetallic strip, depending on where you set the temperature to, will actually either open or close these circuits. So basically, whenever you set the temperature to, what will happen then is that temperature, say, increases or decreases, the bimetallic strip will either go into this direction or into this direction, causing your circuit to either open up or to close, depending on how you have this thing actually set up. So in that case, let's say in the summertime, you want it to close when the temperature increases too much. So in that case, you might have it bent to the side, and then as the temperature starts to increase, this thing is going to start to open up, and as it starts to open up, you have the contact over here, so it's going to close against the contact, causing your AC to turn on, until eventually it's going to cool down enough that this will start to bend away, and as it bends away, it then is going to open up and then turn off your air conditioning. Right? So these are things that this is actually used for. Anyways, so in the next video, we'll start looking at some examples of just thermal expansion. So a couple quick quick examples. So that's actually going to be a very short video. And then from there, we'll start moving on to other ideas in thermodynamics.